So good evening, everyone. Hey. So good evening, and my name is Michael Peskin. I'd like to welcome you to the first SLAC public lecture of the new academic year. Thank you very much for coming. We're very excited in these lectures to share all the interesting things that are going on in this place with you. Before we begin, I just call your attention to this emergency information here. So I have to be like the flight attendant. If there's an earthquake or other disruptive event, the doors are there, the doors are there. Let me now introduce tonight's speaker. So this is, the talk tonight will be given by Dr. Yulin Chen of the Stanford Institute for Materials and Energy Science, one of the associated laboratories to SLAC and the Stanford Department of Physics. Dr. Chen actually was a graduate student here. He did his undergraduate at the famous University of Science and Technology in China, came here to work on X-ray science, got his PhD here very recently in 2008. And very recently, he's become one of the newest long-term staff members at the laboratory. His expertise is angle resolved photoemission spectroscopy. Okay, well, we'll see a little of that during the course of the lecture. He's now known as the discoverer of the things that you will hear about tonight, these magic new materials that Dr. Chen will explain to you. So we're very glad to have you. Thank you very much.
Okay, good evening, everyone. And I'm very glad to be here and to present you some of our recent work on the family of very exotic new materials that have the potential for the future devices. That just like electronics and then the future computer, and then I will explain in the rest of the talk. I believe we all have suffered some or all of these problems. So when you play with your new iPhone and suddenly you realize that you're out of battery, or then you wish your computer can compute things faster than you thought. And also when you go and work out, and then you wish that the MP3 player you bring is not too large, or when you stop at a gas station, you realize that your MPG number is too small. So, and then in the rest of the talk, I will show you that the new type of material, the so-called topological insulators we discovered at Stanford, and then make use of the facility at SLAC here, have the potential to solve these problems. And then this new material, and then which have a lot of potential of applications, and then which can change our life. And for now, let's not worry about these details, figures, and then I hope after the talk, you will understand what they are and then what we can use them for. And then the unique properties of these materials, and of course, the application potentials. So usually, things start with the thinker. So why we need the new materials? That's because we're not satisfied with the current ones. And of course, before we're looking for the new materials, we need to understand what kind of materials we already have. And then whether we can find the new materials that doesn't fit into this category that has the properties that we would like them to have. And then that can change our life. And then in the third part of the talk, I will explain what are the topological insulators. And then how we can find them. And finally, that's the key. That's all of motivation, what we can use them for. So now the first part, why new materials? As we briefly discussed before, that we're not satisfied with the things we already have. And the human history, let's look back, is just a history of using tools and energies for better life. It's true for the Stone Age. It's also true for the semiconductor age. Although the tools we're now using is quite different from what people used back that time. There's a stone axes, the stone knives. Now we have the computers. Yet we are no longer satisfied with the cooked food by the fire. And then we should be very proud that we live in the Silicon Valley, the valley that just grew from the very first HP garage about 70 years ago, and then where they make their first product, the RC oscillator that Walt Disney used for the early movies, and then now it becomes the center of the semiconductor world. And the prosperous of the Silicon Valley is actually driven by just the hardworking engineers, which is governed by this Moore's law, and who is the co-founder of Intel Corporation. And we can see that what the Moore's law says, the transistors in a CPU will approximately double in 2 years. And this trend holds for the last 4 decades. We can see that first Intel CPU, this 4004, has 2,300 transistors inside this, this package. And then now we have the Intel Core Dual CPU. It has more than 2 billion transistors. That's a factor of 1 million. And then this make our life better. For example, like this, the camera, digital camera. Back then, for $100, you can only buy 100 pixels or 200 pixels. But now, with $100, you can buy 10,000 pixels, even more. And also, the size of the camera shrink a lot. And the Moore's law also holds for the computation power. That's this graph will show the calculations per second $1,000 can buy. So in 19th centuries, that $1,000 you can buy, that's one calculation you need to do that in 1 hour. And now it's just less than 1 millionth of a time, of a second. But you also may wonder why we are now hearing the noise, the voice like that. The Moore's law doesn't hold. People start to worry about it because if you think about it, then in 1990 to 2000 years, that the CPU clock speed of Intel's then just changed from about 100 megahertz to 2 gigahertz. But within the last 10 years, it's just all about 2 gigahertz, maybe 3 gigahertz, but certainly not scale like this. So people start worry that this Moore's law doesn't hold anymore. The speed will slow down. Of course, this is not what we want to see because we want even faster computers. And then we want the trend like this. Okay, what should we do? And if you look back into the history, we notice that all this progress is powered by the use of a new technology from the new materials. At the beginning, it's just a punch card to a relay, to the vacuum tube, to the transistor, and now to the integrated circuit. So if we want to continue this trend, maybe we need to find something new. Then we can fill in here to keep this trend getting upward. So that's our motivation. We need to look for new materials. But of course, when we get into a new region, we need to understand what we already have. Then we need to classify our materials and then see whether we can find materials that doesn't fit to any of this categorization, the classes. Then that is possible for us to find the new properties. So for example, like the electric materials, then it's very easy that we know there are conductor, we know there are insulator, and a semiconductor. How can we tell the difference? We know that the conductor, when you just put a battery on, there are electric current. The electron of the conductor like to move in one direction. Then the good conductors include all metals, just like gold, silver, and copper. And an insulator means that even if you put a battery on, there's no current. There's still a lot of electrons moving around the atoms, but they don't move from one side to the other. Then the good insulator include plastic, glass, and wood. And then the semiconductor setting, just this material, kind of like a conductor, but also kind of like an insulator. In the ambient situation, just like a regular situation, when you put a battery on, there's no current. just like insulator. But if you do something about it, you just heat it up, or you just shine a light on it, then suddenly this current flows. So here it shows the germanium semiconductor, and then here shows the silicon wafer where all our CPUs are made on. So now we got a feeling of the difference between conductor and insulator, but that feeling is not enough. For physicists, they want to find a criteria. Say, if you met this criteria, it's conductor. If you met the other one, it's insulator. Then we can categorize our materials much easily. And then our intuition tells us that maybe we can count the electron number. Maybe the conductor has more electrons than the insulator, or maybe something else. But if we look at this picture, that I purposely put on 2 electrons per atom in this cartoon, you can see that even the electron numbers are the same. We can clearly tell one is conductor, one is insulator. So the number of electrons is not a good criteria. And then if we look at the position, we take a snapshot at each time. So it seems that the electron is always everywhere, here, also here. Then the position of the electron is not a good criteria either. So now we start wondering, okay, because the current means the electron flow just go in one direction, maybe it has something to do with its speed. So that's exactly what the physicists introduced. So now since the real space picture cannot tell the difference, what about we move to a new space called momentum space? That's nothing else, just the speed space. First, we explain the momentum is just the speed of the particle weighted by its mass. So imagine that there's a car and a bus. It's running at the same speed. The momentum of the bus is obviously larger than the car. So if they collide, then the car will be bounced back, but the bus will keep going on. But for a same particle like an electron, the momentum is just the speed because the mass is the same. So let's look at this traffic flow pattern of the highway. The left and the right is very clear. In the left, we have a lot of cars going upward, but only a few cars going downward. So we plot this distribution of the car number against its car speed. We have the plot like this. There's a big hump here, means a lot of cars going upward. There's only a small number of cars going downward. That means there was a net traffic flow upside. So let's look at this one. So this is a very busy highway. There's a lot of cars in either direction. And then if we plot that against its speed, it looks like that. There's a lot of cars going to this direction, and there's a lot of cars going to this direction. But if you look at the net traffic flow, there's almost no net traffic flow because they all cancel out. One car going up, one car going down. So there's no net flow here. Then that's exactly what we can learn. What we can learn here can be directly applied to the electric current. So in a conductor, when we apply the volt battery here, then a lot of electrons moving to the right forms a bump here, just like these cars moving upward. And then only a few electrons get scattered back, like this one. It's moving on the opposite direction that forms this distribution here. So that means we have now a net current going to the right. And if you look at this cartoon, the electrons, they're still moving, but their velocities, their speed is everywhere, right? There's electron going right, up, down. Their distribution is like this, just like this highway case. So there's no net current flow. So here we got a sense that this kind of chart, the distribution against the speed can tell us one is conductor or one is insulator. This one, like this, just like the highway case, one is the traffic flow is very smooth, then the other one is stalled. So of course, in the real world, the highway is not only one direction, they're all directions, like left, right, up, down. So imagine there are a junction have a lot of highways, and then these two highways, they're all packed with cars. So from the previous slides, we easily see that the distribution of this traffic is like that. So each direction is symmetric, so they cancel each other. So there's no net flow here. But for these two highways, there's only a few cars there. And then the distribution look like that. Unlike these two highways is filled with cars, this one is not completely filled. Then what's the what this will tell us? In a partially filled highway, if you really want to go home to have your dinner, you can't do that. You can just bypass cars, although we strongly discourage that unless you just do that within the speed limit. But you could. And then this means that some cars, more cars moving to the right, less cars moving to the left. So for this stalled highway case, like there, these two highways, they're still packed with cars, completely filled. There's nowhere to go. And then if the car, well, the car is not helicopter, it cannot fly from here to this highway. So although this highway is empty, so if this car wants to go home to have their dinner, so you can't do that because you have to follow the traffic. You cannot bypass cars like in this case. So in here, now we got a sense. Oops. So that we can use this kind of chart to represent a highway is conducting or not. There's a net traffic flow or not. So like this, there's a highway that's partially filled. Then it can have a net traffic flow. But the highway, all the highways completely filled, or there's no car at all, then there's no net current, no traffic flow can occur. Okay, so this is just like very similar to the concept we will introduce, that the band structure of the materials. It's just a distribution of cars against the velocity. And then you can see in the next slide. Here we plot the same figure there. Now, they represent a different thing. This means this is the band structure that the quantum mechanics tells us that in solid, the electrons like to form electric band, which just like the highway structure, and then the electrons just fill into this highway. And then we can use the same chart to represent this so-called band structure. And then again, we get a similar result. For the conductor, the electron filled half of this, not completely filled this band, but may completely fill other bands. So this not completely filled band can cause the current. If we put the battery here, then the electron move to the right, just like in the highway case. Then there's more electrons which want to move to the right, and then less electrons want to the left. And in the insulator case, it looks like that. So even if you put a battery here, the electron want to move to the right. But because the highway is completely packed, there's nowhere this electron can go. So then there's no electric current. So just immediately we notice that the only difference is just the structure of this one. If we draw this figure, or the band structure of this material, we can immediately tell whether it's a conductor or it's an insulator. So this band structure means the conductor, and this band means insulator. And then we will use this as the criteria, and then we will see how weird the band structure the new material have. Okay, now we understand the existing materials. Now let's get a step further to see what's this new exotic material, the so-called topological insulators. So now we know there's conductor, we know there's insulator, but people start wondering whether an insulator conducts. So what's a nonsense question? The insulator, by definition, it means that it doesn't conduct. Okay, so in the usual case, people will mean that insulator, that's just like this plastic, it doesn't conduct as a whole. But is there any material existing in the world that's in the bulk, it's an insulator, but the surface conducts? So this is a very exotic idea, and even for us. There are smart theorists at Stanford that propose there might exist some of these materials look like this. The bulk of the material is an insulator, but the surface conducts. The electron like to move on the surface. Actually, it's not so exotic. Just think of human beings like us. We like to live on the surface of the Earth. Usually, we don't get into it. But still, for our common sense, it's hard to imagine. The wood, it doesn't conduct So it doesn't conduct in a bulk, and it doesn't conduct on the surface. And the metal, just like a gold, it conducts in a bulk, and it also conducts on the surface. So it's this strange thing that conducts on the surface but not conduct on the bulk. Yeah, we spent a lot of time thinking about that, and then until finally we found such kind of material as SLAC. But before that, let's see what's the band structure of this material look like. As we just saw, this band structure of a conductor, we have two bowls, one of here, one of partially filled, that's conductor. Insulator, we have one completely not filled, and the other one completely filled. And if this kind of thing, topological insulator, really exists, it ought to have this kind of band structure that has something in the middle of these two bands that looks like a cone with a knot in the middle. So this exotic thing's never been observed before. And then there's a theorist that said they exist, but as an experimentalist, it's hard for us to imagine, and then we need to do experiment to prove its existence. And then before we get into the details, let's show how different they are. So imagine that this one, if we want to change that to the insulator, there's no way unless you really cut this conical-like thing. And then if you want to make it into a conductor, there's no way because there's no electron in this bowl. So it's different. This material is different from the conductor, is different from the insulator. So it's a brand new material. It cannot be classified as any of the known things we knew before. Okay, so then why we call this thing topological? Insulator, why don't we call just an insulator with a surface conduction or something? But because, not only because it looks cool, but also because it's actually have some similarity with the different topological subjects we knew. Because here, if we don't cut this magenta thing inside there, we cannot change that into a regular insulator. And it's very similar to the sphere and torus, right? Imagine that a sphere made of the rubber, you can just deform it, you can just stretch it, but you cannot make a sphere into a torus until you cut a hole in the middle, and then paste that hole, and then you can get a torus. But that's too violent. We don't like to do that. Yeah. So we know that these two different subjects, we call that topologically different. That's they have the different topology. So that's very similar here, right? Because in the topological insulator, you cannot deform this one into that unless you do something violent. Let's cut this one. So that's where the topological comes from. Okay, now we understand the band structure. There's one second concept we would like to introduce before we can fully understand the topological insulator, the material. That is the electron spin. So we know all the electronics, we make use of the charge of the electron. The electric current is just the motion of the charge. The electron is moving, but it carries charge. That's why there's an electric current. But we know that the electron doesn't only have charge. It also spins. It likes to move, just like the Earth. The motion, the spin of the Earth causes the day, right? And then also the solar system is spinning by itself. So that's not very exotic. So also we know that when there's a spinning of the charge, it will produce a magnetic field, just like this one. So the spinning of the electron just makes this electron like a small magnet. The small magnet does something interesting, that the magnet, you can define the north and south pole. So the magnet is different if you have different directions, north and south. If you flip it, the magnet is not the same as the original one, right? But then for a ball, it doesn't really care, facing up or facing down. And then you might think that the concept of spin is very elusive, but we do have some application that we use every day that make use of the properties of spin of electron. That is hard disk. So when you uncover the hard disk, you see there's a disk, and then you have a read and write head. And we zoom in this read and write head, Then you see there's a coil. You can just apply currents to generate a magnetic field to flip the spin on the disk. That's how we save all the information, including these PPT files, into the hard drive. Right? But you may also realize that for a laptop, the hard drive is the single largest components. Well, let's not talk about the screen or the keyboard. Just like the ICs, the hard drive is the biggest components. That actually limit the size of the laptop. And then we will see that how this topological insulator have the potential to make a small hard drive. Okay, then the spin in topological insulators, well, this means topological insulator rather than the Texas Instrument. So there's a perfect lock-in between a spin and the electron momentum. So this looks like that. So it's just like a disciplined troops. So electron moving to the right, the spin has to pointing down. And the electron moving to the left, the spin has to pointing up. So you think, what's the big deal of it? If we look at the regular material, it's not like so. So in a regular material, the spin just like you throw a lot of small magnet into a box. The magnet just like to have all the directions that each of them likes, right? So that's why in this animation we didn't put the spin direction because they are random everywhere. But for topological insulators, this is not so. The electron like to be ordered. And then we will see that this order will make it very important to make a new type of device called spintronics. And of course, also, this locking of the current spin has a very deep aftermath. Is that the no U-turn rules for electron. So electron, just like cars, is moving in either direction. But what if the cars hit a bump or hit a wall? It will bounce back, just like the electron will do in the regular material. But let's take a look at this carefully. That in the topological insulators, as we just know that there's a perfect lock-in between the current and the spin. So the electrons move in this direction, spin is pointing down, but it gets scattered back. The spin has to pointing up. The spin flips. But we know that the magnet, if this impurity is not magnetic, it doesn't flip the spin. So you flip the magnet by another magnet. If you put a magnet here, then you put just a metal close to it, a plastic, the magnet direction doesn't flip. So that means if this material, you put a lot of impurities there, as long as it's not magnetic, this process doesn't happen because it's against this perfect lock-in rule. So the electron cannot U-turn. So it cannot be scattered back, be bounced back. So what's the meaning of this? So we know that then if we have a car easily get bounced back by something, then we cost a lot of energy to do that. Then you need to move back forward. And then if there's no U-turn, the electron is very smart, just like a water flow around the pebble. It just keeps moving forward. So that you save a lot of energy. The energy the electron carry is always moving to the right, used to move to the right. There's no back U-turn. So then if we use this kind of material to make the conductor, it can save us a lot of energy, as we will say later. So, and then what we can use on the topological insulators, that's I just briefly introduced that the device consumes less energy because the no U-turn rule. And then the higher density of IC circuit we will see later. And then also spintronic device we also briefly discussed. And then the efficient thermoelectric material, and we will also discuss later. But so far, we think we have enough motivation to look into this kind of material and run some experiment. Because after all, the experiment is much harder to do than just sitting on the computer, get the idea. So the theorists got maybe one day work to find the idea, and then experimentalists maybe take a month to verify that. Okay, so do topological insulators really exist in the nature? So as we just saw that this material is kind of exotic, so nothing simple can happen. So for the simple elements, none of them are topological insulators. So for the simple elements, we have metals, we have insulators, we have semiconductors, but we don't have topological insulators. That's why people didn't know that before last year. So, but the smart guys, some smart physicists, and including one sitting back in the last row here, they did a calculation and then say that, predict that the bismuth telluride or bismuth selenide and antimonide telluride, these compounds, they are topological insulators. And then this is the nice crystal structure out of it, of the bismuth telluride, and then this the real sample we grew. It doesn't look so nice, but anyway, it has a very nice properties. So you can't judge a person with the experience. You can't judge a material with the experience too. So and then if they calculate the band structure of this material, it looks like a nice, very beautiful flower. It doesn't look like the boring, just a highway, just a band structure we just saw for metal, for conductor or insulator. It looked like a flower. The key point is that the flower has these knots here. They converge to one point, as we saw in the topological insulator band structure. Okay, and as experimentalists, and then it's now our job to see whether this is true. Okay, then we go to the fourth section, fourth part, how we can find them. Okay, the technique we use to check the band structure is so-called the photoemission spectroscopy. This is how we can see the band structure of electrons. Then how do we do that? So when we have the photon coming, then electron is kicked out by this the lights. And then these electrons, we can collect them with this electron analyzer, and then we can collect its speed and then its direction. So we know that speed times the mass is just a momentum. By using this technique, we can calculate how many electrons in this momentum and how many electrons in the other momentum, and reconstruct the distribution of the electrons in the momentum space, which is nothing else but the band structure. So that's why we spent a lot of time explaining the band structure. That's only because what we can measure in the real world is the band structure rather than the electron position inside the solid. Okay, so for the three-dimensional band structure, unfortunately, the cutting-edge technology nowadays can only sample a two-dimensional cut out of it. For example, like a three-dimensional feature, we can only sample along this direction and then get a circle, or along this direction and get a parabola. So what we need to do is to sample a lot of this slice and then assemble them and then reconstruct the three-dimensional band structure, and then compare those to the theoretical calculation. Then where do we do that? We do that here, right? That's why we give a talk. Then we are here in this auditorium, and the experiment is done in a SSRL, the Stanford Synchrotron Radiation Lab. That's also a branch of SLAC in the other corner. And then if we get rid of the roof of the SSRL, it's just like a ring inside here. There's a lot of dots. It's not a pin. It's just it's the end station, and I will blow up that in the next slide. But the function of this SSRL is to produce the lights we need to use for the photoemission spectroscopy. How it does it? It just have the electron circle in a ring just again and again, and when it has enough energy, it gets to this large ring. When you bend these energetic electrons, and it shoot out photon lights. And then this shows you how the photon generated by the electron. So when electron is jiggled away, find its way through the so-called undulator, the lights will come up. And then photoemission spectroscopy make use of these lights. Okay, so if we blow up these small dots here, and it become an X station. So to show the dimension, that if I stood here, I will only reach these points. So this is just more than a regular room size N station. Well, it's just an all metal or maybe cool machine. So here is the cryostat manipulator where we transfer the sample into this vacuum chamber. And then this is a preparation chamber if we want to do something on the sample. And then this is the electron detector, the large, the dome-like the thing. And then we put the sample here. We put the sample on the manipulator and then just move them into this analyzer chamber. And then there's a photon comes from this ring. We shoot the sample, kick out the electrons, and the electron get detected by this detector, and then we get a two-dimensional slide of the band structure. And then when we do the experiment, this thing, the whole thing will move. It's about 2,000 pounds. And then because we just know that we only get two-dimensional information, but we need to reconstruct the three-dimensional, that's why we have to rotate it and then get the many two-dimensional cuts and then reconstruct it. Okay. And then this shows an example on how we get the real data. Then the two-dimensional cuts, we just keep doing this, keep rotating it, and then you see that we can just reconstruct a three-dimensional feature. And in this case, it's still a very crude sampling. But if we just rotate this analyzer very slowly, and then we make the sampling along this direction very dense, then we can reconstruct this band structure like this. You immediately realize that it looks so like this theoretical prediction. It's almost identical. There's a flower here, and then the key point is just a knot of electrons, and it's here. So along each of this line, the electron have the same spin as we knew just now. Okay, so after got this data, we immediately realized that we found it. We found this new material, the topological insulators. And then usually the beautiful things is very vulnerable, but that doesn't apply here. This beautiful flower is very robust. We know that usually the surface is vulnerable. For the iPhone, you easily scratch the screen, and then anything you easily scratch the surface. And that also applies to the material, materials. If there's a material, the surface is electrons move on the surface like a conductor, you can easily destroy those surface electrons by just throwing a lot of dirt on it, just like oxygen. It will oxidize the surface, just like aluminum. Aluminum is a conductor, but the surface of aluminum is aluminum oxide. It's an insulator. So we try to destroy this one and see whether it's really different from anything we have known. But we were so surprised to find out that we cannot destroy this flower, no matter what we do. Like oxygen, we dump a lot of oxygen on the surface, hydrogen, carbon oxide, carbon dioxide, and potassium. We put on it, and then we measure the band structure. They all look the same. That means the surface electron is very robust. It just like to go through on the surface. No matter what you do on it, it's there. That's just like the no Newton rule, because the spin has a definite correlation with its momentum. If you want to scatter it, there's no way unless you put a magnet there. But these things are not magnets, so spin electron carry spin just find its way to get around all the dirt and then keep moving forward. That make this flower robust. So this property is very important, as we will see later how we can use them. And then, yeah. Okay, now, at least to me, I think anything we found should have some use. I don't like to work for years and years and then to find out something that's useless. So I hope that this topological insulator we found can make new devices and contribute something to our lives. indeed, with all these nice properties we just discussed, we can make a lot of use of them. And then here are a few examples. First, that we can easily make electronics consume less energy. That's because of this no U-turn rule, as we already know, because although there's some dirt on the surface, the electron likes to go around it, and that doesn't dissipate energy, doesn't lose energy, you just keep carrying on. And then you see, even for the purest silicon crystal nowadays, we know there's a lot of defects on here. That's just like a dirt. The electron travel on the silicon. It easily encountered these defects and got scattered back, got bounced back. But for this material, this kind of defects cannot bounce the electron back. So topological insulators can easily make devices that consume much less energy than silicon. So later on, you don't need to worry about how many batteries you need to bring with your boombox or something. Then you can just carry one or two, and then it lasts longer. Also, and then we can make the electronics even smaller than current electronics. And then we know that the magic of the computer is just based on the concept of scaling down technique. This is the first transistor Bell Lab invented in 1940s. And now we know that this transistor is just one of the 2 billion transistors in a CPU chip. So the size shrink more than a billion times. But we realize that in this case, we still use the 3-dimensional material to make the transistor. And 3-dimensional scaling factor for a 3-dimensional material, that's the so-called scaling factor, is inversely proposed to its volume. So the volume gets smaller, it gets worse, because imagine there's some defects in the material. The volume gets smaller, the possibility that a transistor have one of these defects, the possibility increase dramatically. That's inverse proportional to its volume. But if you think about this surface, if we use a surface to make a device, and this scaling factor is 1 over its area, that is dimensional to the second. If we plot these two factors in one graph, it looks like that. This is a 3-dimensional material, the scaling curve. This is a 2-dimensional scaling curve. And then here is a device dimension, and the vertical axis show you how possible the device will fail. So of course, for any given device, we have a tolerance for the failure possibility. So beyond this possibility, it's not acceptable. It's a defect device. But below that, it's OK. So we draw a line here. And then immediately, you see that this line intersects at different position for the 3D and 2-dimensional case. And remember that 3-dimensional is a current technology, is a 2-dimensional is a future technology. And then easily you find out that for the 2-dimensional technology, for the topological insulator case, then the device dimension can be much smaller than the 3-dimensional technology. That's what we are using now. So this tells us that if we use this material to make devices, we can make them even smaller. And then in one CPU, we can have more transistors. And also, this perfect locking of the spin just make it possible to manipulate this spin without the use of magnet. In our conventional thoughts, we always thought that we need to use the magnet to drive another magnet. But this tells us no. If you have the current moving this direction, the spin just like to go to the other direction. Just like the current in this special material, the current can drag the spin. So without using the magnet means a lot, because as we already realized that a hard drive is the largest component in the computer. That's because it has to have a read and write head. That cannot be made small. So now without using this one, we can use the electric current to control it. Electric device can be made a lot smaller. That's just like a CPU. And then also, this perfectly ordered spin can be used in a brand new design of a computer, so-called quantum computer. And then in this new concept, this new computer design, and then by using the spin to store information, and then demonstrated theoretically that it can be easily 1 billion times faster than a current computer if you want to crack a 64-bit password. So that means then usually the task you need to do for thousands of years, now you can do within 1 second. So now with this nice property, the so-called spintronic device just the device make use of electron spin, can be much faster than a current device, can be much smaller, and also can consume less energy. Also, finally, this material can make very good use of energy because we realize that it consumes less energy because of no Newton rule. But interestingly, this material also generates energy. So if you heat the bismuth telluride, this topological insulator in one side, magically it generates electricity. And then so these nice features then we can easily find use for them. For example, like in a car, we always talk about our MPG problem. That usually the MPG now is about 30 miles. It's a pretty good number. But still, there's a lot of heat wasted in the engine because the exhausting gas is very hot. That contributes partially why the warming of the city. And then, but imagine that we put this material into the muffler, then it will harvest this wasting heat, and then turn it into electricity. We can put it back into the car system, and then just to, for example, like use the motor to drive the car, then it saves a lot of energy. Then that will dramatically increase the MPG number. And also, in a satellite, it's really a lonely star. You cannot plug the power cord here, so it almost solely rely on a solar panel. But then sometimes the solar panel doesn't generate enough power because solar panel, the efficiency only 15%. So that means 85% of the sun power turned into heat. But now we already found a material that can turn this heat into electricity. So we can use this in the satellite or the space shuttle and then generate the electricity for their use. And also in some part of the Earth, there's a lot of wasted heat here. That heat makes the soil unsuitable for plants, and we cannot grow plants there. But with this material, we can turn this wasted area into a power plant and get the energy from almost for free. And that very interestingly, so this material can turn heat into electricity. It can also turn electricity into coolness. Then it can move the heat from one side of the material into the other. So imagine that now we can make a refrigerator out of this bismuth telluride. And then what is better than a current refrigerator is that it's completely silent. There's no noise because there's no moving parts. You just put electric current there, and then you just make the thing you put inside there cool. So then in the previous slides, I show that this material can really be applied to the life. Then the device consumes less energy, spintronic device without using magnetic field, or the high-density IC chips or efficient thermoelectric materials. Thermoelectric material, just like in the previous slides, that can turn heat into electricity and turn electricity into coolness. And then here are just a few examples. I hope that you can think more than I have yet thought about. And then we hope that this new material will fill into this blank and then keep this up, the Moore's law going in the next few decades, and keep the Silicon Valley prosperous, and also move our world into the spin age, maybe. Okay. And with this, I thank you for your attention, and all my colleagues in Stanford Institute for Material and Energy Science. And thank you.
So thank you very much. We have time for a few questions, and I guess, sir. Yulin, I ask you to repeat all the questions to get them on the microphone so people can
sure. I will try.
I have two questions, a chemistry question and a supply question.
Okay.
So the chemistry question is it an easy, low energy, inexpensive, clean process to make the bismuth telluride?
So this is a very good question. If that's just very expensive, then it will cancel out all our efforts. And fortunately, it's not very expensive. Bismuth is a very abundant material in the world. And then you can buy in pounds for tens of bucks. And the telluride is slightly more expensive, but it's less expensive than the regular precious metal like a gold. But it's a similar size, similar price as a silicon. So, yeah, if we make use of the bismuth telluride, then the price won't be higher than the current technology.
And to put those things together and make the bismuth telluride, is that easy and clean?
Yeah, in that part, then we can answer very definitely. That's very easy.
Good. Thank you.
Oh, yes. Right. Sorry.
Okay. Sir, please.
I was going to ask you about liquid metal, the company that Apple bought.
Liquid
Metal.
Liquid metal.
If you're familiar with it. I think it was zirconium. It's similar properties, topological insulator. You can pass it's bulk amorphous metals. Zirconium and something else. It's tried since 2002. about 8 years ago. And one of its properties is you get surface conduction, but insulating through the bottom here.
So your question is that there's a liquid metal. What's the difference between this liquid metal and the topological insulators?
Liquid metal it's a bad name for it. That's what.
Okay. So liquid metal, it's an insulator in the bulk, and it conducts on surface. So this has a very profound difference between that and the topological insulator. The topological insulator, that it conducts on the surface, but this conduction is very robust because it has this no U-turn rule. For the liquid metal and the regular metals, this rule doesn't hold. The electron easily get bounced back, and then so this is just like a regular conductor that just make it very thin. Yeah, and then also the spin doesn't have a definite direction, and then it cannot be used as a spintronic material.
Okay. Sir.
What kind of efficiency are you getting on the heat, the current transfer?
So the question is, what's the efficiency of the heat, the electricity cycle? So currently, it's about less than 10% in a bulk material. But then, because this topological insulator has a very robust surface state, and then we know that when we make this material very small, this surface to volume ratio will be greatly enlarged, like a nanomaterial. And then it has been shown theoretically that when we make the topological insulator very small to the nanoscale, then this efficiency can be improved by a factor of 10. So that's more than 50%. But that's a theoretical proposal. We definitely need to do experiment to find it out.
Okay. Sir, over here, you've been waiting.
What happens in a strong magnetic field?
So a strong magnetic field, this is a very interesting question. And at the strong magnetic field, the surface will be, well, the so-called gap. That means because you have a magnetic field here now, the magnet can be flipped. So it can be bounced back. So this actually is not a bad thing. You thought it's a bad thing that the electron got bounced back. So it's not, because we know that this surface, we always talk about it, it's very robust. You always like to flow currents. But to make a device, sometimes you want a switch. You want electric current to flow or stop, just like for the lights. So the magnetic field can use as this switch. And this actually is a result we just published in this year's Science magazine. That if we put magnetic impurities into the material, it will break this robustness of the surface conduction. And then this is a very, very nice property. We can use it to control its conduction.
Sir.
So what's the difference between this and a Peltier device in the example of using it for generating energy from a temperature difference and creating a temperature difference from electric power?
Pulsated device.
It is basically a Peltier junction, except.
Oh, I see. So the Peltier junction, that's one of the early generation of this.
So please repeat the question.
The question is that what's the difference between this material and the Peltier junction? That the early generation of the material that generate heats, electricity from the heats. So actually, those. So we know. Let's start answering this question from the other angle. That we know that there's things called thermocouple, that we measure the temperature using thermocouple. That means that we have two different types of the metal and connect together, and then if the temperature of these two metals is different, then it generates the voltage. So that is similar, but also different from these applications.
But also, you can put power on it, and it creates a temperature difference.
That's right. So the difference that in that process, the power it generates is very tiny. And then in this case, it's substantial. You can really use them. The efficiency is very different. So that's the main difference. And then, yeah, if we have time later, I will explain the physics principle underneath it to make this difference.
I have two questions. One of them is, so I know now that computers and their heat is a real problem with this new technology. Would that make it so that the heat inside of a computer could be more of a valuable resource rather than a hindrance to the progress?
So the question is that whether this material will just make the heating problem of the computer less? Is that?
Yes, to take the heat of the computer and convert it back into energy.
Definitely. That's, you can just put this material on the top of the CPU, and then you can just get that heat. And it cannot convert those heat 100% back to electricity, but it can convert a big portion of it back to electricity. Yes.
My other question is, how soon do you think that we could be able to see this material being sold on a market?
So actually, this thermoelectric application, people already realized it. And then you can already get one of this CPU heat sink made of this material in the market. Yes.
Yes, a twofold question. How and why were the two elements, bismuth and tellurium, selected for this material? And are there other combinations of different elements, either binary or tertiary, on the horizon to make
Okay.
advancements?
The question is that whether this bismuth telluride compound is unique, or whether we can make other topological insulators, binary or ternary, from the other elements. The answer is it's not unique. The answer is yes, we can make more topological insulators. For example, recently we the theoretic predicted and also experimentally proved is that the ternary compounds, the thallium bismuth telluride, is also a topological insulator. And in this family, not only bismuth telluride, bismuth selenide and antimony telluride, they are all topological insulators. And also the thallium bismuth telluride, thallium bismuth selenide, and they are all topological insulators.
But so far, all the examples come from this neglected area of the periodic table.
That's correct. The fundamental reason is that in this kind of materials, there's a so-called very spin optic coupling inside this material. This causes the band structure of the material inverted. So it's very different from a regular material. This inverted band structure provides a ground for the living of this surface, very unusual surface state. So in a regular material, the band looks all normal, like in a metal or insulator. So it doesn't happen there. Only in that portion of the periodic table, we found this phenomenon exists.
So let's take two more questions.
the question is how can we write a pattern and read something just like a hard drive, right? So in this case, then the hard drive is no longer as its current form. It doesn't need to have a read head or a write head. So it's just, on the other hand, it will more look like a field effect transistor. You just control it by electrically. Then you can measure that's its on or off state. So that's the key why we can make the device smaller. If we still have this read head, then it will move around the disk, then the size won't be shrink too much.
And last question up here.
So when you build a switch out of these, do you expect to be able to scale them as smaller than contemporary transistors? Or is there a reason why they might not be quite as small?
So I don't see a reason why it cannot be scaled down to as a regular transistor, because we already are making the devices at 15 nanometer in size or less. So the current, if we read the news that the Intel CPU now is a 35 nanometer, but then we already make 15 nanometer, and then we see the surface, the topological property is very prominent. And we can only imagine when it gets smaller, it will be more prominent because the surface to volume ratio increase. And the topological insulator, the magic is on the surface. So
the fundamental size that you can shrink to might be smaller for these eventually.
That's correct. So the only limit we know now is just the bismuth telluride. Each layer of material is a layered material. And each layer is about 1 nanometer in size. As long as we are 10 nanometer or more, we should be safe. Yes.
Okay. So let's end the public question session there. And let's thank Yulin again for this beautiful talk.
Thank you.
Now, as always at these events, some members of the staff of SLAC hang around, and you can recognize us by these lovely helmets. In particular, up in the back of the room, actually they'll be out in the lobby. There's some other people from the SIMS lab who can answer your technical or more detailed questions about this talk. And as for me, oh, I'm sorry, this is not my field, but you can ask me anything else. And Yulin will be down here. And finally, let me just say that the next of these events will happen the Tuesday after Thanksgiving, and that will be in a totally different realm. We'll tell you the latest news from the Large Hadron Collider. So see you all then.